Welcome back, fellow engineers, control room operators, and, well, anyone fascinated with thermodynamics. Have you ever wondered what's really going on inside the digital brain of your power plant when the physical sensors just start to drift? Today, we're taking a deep dive into an incredible dynamic diagnostic tool that's actually hidden right inside your steam turbine's control logic. In this explainer, we're going to unpack the elegant math that literally keeps the grid stable and your turbine spinning, even when things look a little, let's say, off on those control room screens.
Okay, let's look at the game plan for this explainer. We'll start with the load estimation equation itself. Then we'll calculate a baseline load, decode a really interesting operational anomaly where 82% somehow equals 100%, and finally, look at dynamic system pressure shifts.
All right, kicking things off with Section 1. The load estimation equation.
So here is the core equation. It simply states that your estimated load is approximately equal to your control valve flow coefficient multiplied by your main steam pressure. But listen, I really want you to understand that this isn't just some static formula slapped into a textbook. It's an active, living approximation driven by physical laws, specifically Stidl's ellipse and the principles of stage pressure. It's basically the control system's way of mathematically modeling physical steam flow in real time.
Real quick, before we start throwing numbers around, let's calibrate our terminology so we're all on the exact same page. MCR stands for maximum continuous rating. That's the absolute maximum electrical load the unit can safely and continuously sustain under its design conditions. And CDFC, that's your control valve flow coefficient, which represents the effective opening area or flow capacity of your high-pressure control valves.
Now, to truly grasp why this works, we have to connect that digital math to the physical reality of the plant. In a steam turbine, electrical power output is directly driven by the mass flow rate of the steam physically hitting those blades. And mass flow rate, well, that is directly proportional to two things: the inlet pressure pushing the steam and the effective area of the control valves letting it through. That is exactly why multiplying valve position by pressure gives us such a highly accurate load estimation.
Moving right along to Section 2. Calculating the baseline load. Let's do some control room math.
Consider a standard power plant with a design baseline of 600 megawatts. That's our 100% MCR. Its rated main steam pressure is 24.1 megapascals. But let's look at our current operation. We've lost our load value on the screen. What we do know is that our main steam pressure has dropped to 19.28 megapascals, and our control valves are sitting at 80% capacity. So, how much power are we actually making right now?
Let's build this step by step, tracing the exact logic your distributed control system runs every single millisecond. Step 1, we convert our current pressure into a percentage of the rated pressure. So 19.28 divided by 24.1 gives us exactly 80%. Step 2, we apply our equation. 80% valve flow multiplied by 80% pressure gives us an estimated load of 64% of our maximum continuous rating. And finally, step 3, we multiply our 600 megawatt capacity by that 64%.
Which brings us to our real-time output, 384 megawatts. Boom! The math holds up perfectly. We can all breathe a sigh of relief instead of watching the shift supervisor panic over mismatched numbers on the board.
Now, you might be wondering, why do we even care about estimating load when we have physical megawatt meters right there on the generator? Well, here's the so what for you engineers out there. Sensors fail, wires short out, it happens. If your control system suddenly loses its megawatt feedback signal from the electrical side, it would normally fly totally blind, but because of this exact thermodynamic equation, the system instantly calculates a backup. It literally saves the plant from tripping by knowing roughly how much power it's making based purely on hydraulics and steam conditions.
All right, on to Section 3, decoding the 82% anomaly.
This brings us to the climax of our explainer. Imagine you're sitting at the operator console and the numbers just do not make sense. Your main steam pressure is sitting perfectly at its rated 245 bar. Your generator is humming along, putting out 100% maximum continuous rating, but your control valve flow reads only 82%. Wait a minute, mathematically, 100% does not equal 82% times 100%. So how on earth is this plant generating full power without fully opening its valves?
Well, this brilliantly illustrates a fundamental principle of turbine design. Your turbine isn't maxed out at all. Actually, it has a highly efficient 18% reserve built right into it. You see, manufacturers almost never design control valves to be 100% open just to achieve 100% load. They build in what's called a valve wide open, or VWO, margin.
There are 3 specific engineering reasons why this 82% anomaly happens and why it's actually a sign of a very, very healthy power plant. It comes down to that valve wide open design margin we just mentioned, the nonlinear calibration of the flow curves, and highly favorable thermodynamic conditions. Let's break down those last 2 real quick.
This next part is a massive point of confusion for new operators. CVFC does not mean the valve stem has physically lifted exactly 82% of its maximum stroke. No, it represents the flow coefficient, or CV. Because steam flowing through a valve is incredibly nonlinear, the control system uses a characterized curve. So this reading simply means that at 82% of the theoretical maximum flow capability of that valve body, you're already passing enough mass flow to generate 100% of your rated megawatts.
Furthermore, there's a huge thermodynamic insight here. Mass flow is driven by pressure and temperature. If you're hitting 100% load with only 82% valve flow, your main steam is very likely at or slightly above design enthalpy, meaning its total heat energy is totally optimal. You've hit the ideal temperature and pressure boundaries, which means your turbine is extracting way more work per kilogram of steam. You are running incredibly efficiently without straining your hardware one bit.
And that leads us perfectly into our final section, dynamic system pressure shifts.
What's really fascinating is how a tiny shift changes the whole shebang. Let's introduce a new scenario. Your physical MCR limit remains fixed, but your actual load percentage shifts. Let's say your main steam pressure bumps up just a little bit above its rated 245 bar, settling at 247 bar. At the exact same time, your CV flow drops to 78%. What is your actual real-time load now? Okay, let's methodically trace the calculations again. Step 1, we find our new pressure percentage. 247 bar divided by the rated 245 bar gives us 100.82%. Step 2, we apply our trusty load equation. We take our 78% valve flow and multiply it by our 100.82% pressure. The result? The turbine is currently operating at exactly 78.64% of its maximum continuous rating. The logic adapts seamlessly to the shifting parameters without skipping a beat.
So the crucial point here is understanding the actual physical reality behind these shifting numbers. Why did the valves drop to 78%? Well, because of sliding pressure. When the pressure bumped up to 247 bar, the steam density increased, and denser steam means a higher capacity to do work per unit of volume. So to maintain a stable mass flow for that specific load demand, the valves automatically throttled back. The math is literally just a reflection of fluid dynamics in action.
Which leaves us with something to think deeply about before you log in for your next shift. We just saw how a slight bump in pressure forces your valves to gracefully throttle back to save energy. But let me ask you this. What happens if you experience a sudden, unexpected drop in enthalpy from your boiler? How violently will your control valves have to swing open just to keep your megawatts from completely crashing? The math is always calculating, right? But it's up to you to understand the actual physics driving it. Until next time, keep your parameters stable and your margins healthy.